My name is Naoya SAKAMOTO from Hokkaido University. I'm studying the solar system formation so using the isotope microscope. So I am also working with Professor Kudo to visualize O17 for biological samples using this machine. Thank you very much for giving me this opportunity. And congratulations for these promising techniques. I am very happy if you could relax and enjoy my talk. This is kind of a Cosmo. Yeah, I start from basic things. Elements are formed in stars. Even for the same element, isotopes are synthesized by different pathways, completely different pathways in stars, depending on the weight or elemental composition of the star. The synthesized isotopes are ejected into space as dust when the star dies. Eventually, the dust collects to form new stars and planetary systems. Therefore, isotopic compositions can be scattered to reflect the original stars. This is the oxygen isotopic composition of our solar system. Not very scattered. Y-axis is isotope ratio of O17 expressed here, and X is O18. And boiling or evaporation or some other thermodynamic reaction should make a line with a slope depending on the mass differences. Taiyo Nissan person, he teach me your O17 water contains much O18, so you don't need to buy O18. so oxygen isotopes of our solar system are plotted on this strange line. Yeah. Oxygen isotopes of asteroid Itokawa brought back by Hayabusa mission or Hayabusa 2 mission close to the Earth on this line. So oxygen is third abundant element in the solar system and the most abundant in the Earth. So this mystery is a kind of one of the biggest problem in our field. The O16 rich end member is Sun, measured by NASA Genesis mission, collecting solar wind in the in some point, long time. And another end member is found in the meteorite as a reacted residue with water. So now people believe our solar system is formed by mixing of water and the bulk solar system. Therefore, solar system evolution can be understood as water evolution. However, our astronomer, could only know reacted residue with water because we still have we cannot obtain water because Earth is water planet. So it's very difficult to get pristine water. So the water itself is still unknown. If we can measure extraterrestrial samples under cryogenic condition, keeping the water as ice, we can know the water evolution in our system directly. This is my motivation for the cryogenic. So this is a photo of isotope microscope to image the isotopic distribution of the solid surface. I don't touch the detail, but it's a kind of a mass spectrometer using a sector type magnet. MRI also uses magnetic power, so it's very close. So this machine can make images. The scale bar is 10 micron. This is meteorite. If we use this machine, we can separate the mass contained in the mass by magnet individually. Then, if we make isotope ratio image, we can distinguish the isotopic ratio difference in this level. So this is another example of meteorite. We can obtain oxygen isotope images of O16, O17, and O18. You can find a strange hotspot in O17 image. Scale bar is 10 micron, so this is kind of a 1 micron grain or something. So in the solar system, we cannot produce this kind of grain because of its very large isotopic anomaly. So now we believe this grain formed in the star, different star. So 10 years or 15 years, I spent. Recently, we succeeded to develop a cryogenic isotope microscope consists of these components. The cryo stage is cooled by liquid nitrogen, and your frozen samples can be introduced into this machine without exposing to the atmosphere. This is a flow of cryoanalysis. First, after surface preparation, sample preparation, and conducting film coating performed in a cryo environment, and the sample is set in cryo holder and transported in a container filled with liquid nitrogen and stored in the cryo airlock. Then measure. We can analyze your frozen sample automatically in an overnight run. We can sleep. This is sample preparation system. All processes are performed under cryo condition. Professor Kudo helped me to complete this system. Thank you very much. So now I am developing a cryo cutting and polishing system for solid material, like meteorite or sample return from asteroid. And this system may help Kameda sensei to cut the skulls, Onodera sensei to cut the bone and polish in the liquid nitrogen. Liquid nitrogen is like, we can use liquid nitrogen as a water under low temperature condition. So a few years ago, we held a workshop on preparing frozen samples to observation with isotope microscopy. Many people attended. Kameda sensei is there. At that time, Kameda sensei provided an example. One of the demonstrations included imaging of the liver. Of course, you are professionals, but we injected water labeled with O18. Then, actually, at that time, this seminar should be finished at 5 o'clock, but they bring me this sample 4:50. So, but anyway, we have done some analysis. This is a isotope image of O16 and 18 and isotope ratio image. You can see bright spot, bright area and not bright area. And if you see on the isotope ratio image, red means O18 rich, means a kind of a vessel, maybe cutted vessel. Here or here. This is vein. This is vein. Then, and also we can see some gradation from the vessel to vein. So this takes kind of I don't know 6 hours or 8 years, 8 hours after 5. Okay. Now I am working on another project also. Earth. This is inside interior structure of Earth. So the Earth core, Earth metallic core, should contain something based on the seismic wave data. But this inside of the core is a terrible condition. So we cannot get this sample. So, but we can reproduce this condition using very small device. But in order to measure the experimental sample after high pressure and very high temperature, when we open this device, everything is 1 atom, room temperature. So all elements distributed. So you can see this is this is a metal core, but nothing here. Metal cannot keep not many things under the 1 atom. So escaped. So we put the device keeping the pressure. Then we opened this device in the liquid nitrogen. Then we pick up the sample. It's a 3 millimeter diameter. Then we put the sample to a cryo holder, and we measure the 3-dimensionally. I cannot show you the hydrogen data or other things. We are preparing the paper, so this is I just show you the ion. This is ion is coming. This is the size is about HeLa cell. This one. This is about the HeLa cell size. So this project cited A+ last summer. Now, cryogenic isotopes can be used for several fields. Thank you very much.